All right. So quick look at the calendar. So project is due today. We're going to cover 3.3. We're going to take a couple days to cover 3.4, and then on Thursday there's a quiz and representative problems from 2.8 to 3.4 are going to be due that day. We may start a little bit of 3.5 on that day, depending on how things go. And is something going on Wednesday? I think there's a majors day up at the U or something like that. So if you happen to not be here, I think we'll get through enough of 3.4 that you'll have a flavor for how things need to go. And then if you need to pull up the lecture and watch that for Wednesday, that would be good. But this quiz right here does cover all the differentiation techniques that we've learned from 2.8 all the way through 3.4, including 3.4. So make sure that you've got what you need in order to do well on that. That quiz will consist of probably 5 problems. Just here are some functions, find the derivatives. Okay, that's it. Okay, show your work, simplify to a reasonable degree, all that sort of stuff. And then we've got our exams on this coming up in about 3 weeks or so. All right. Any general questions? Okay. Then let's get started on this next section. I apologize. My fault. This has happened twice. I didn't check to make sure somebody didn't leave colored paper in the copier, but you got yellow today, but we'll live with it. Okay. All right. So when we're done with Chapter 3, so this is all about what Chapter 3 is, you'll need to be able to differentiate nearly any function. So any of the functions that you've dealt with in math up until now, we're going to be able to find the derivative, even the really complicated ones. If you take a log and multiply it by a trig function and throw a square root into that trig function, we're going to be able to find the derivative. Okay, so about any function I could give you, you better be able to find the derivative. Okay, you got to understand what the derivative means, and you need to be able to apply that and its meaning to real-world problems. So we've done the exponential function. We did product and quotient rules. We did some really simple things like power rule and constant multiple rule and the derivative of a constant is 0 and stuff like that. Okay, we're going to add trig functions to that list of functions that we can differentiate. But we need to go over a couple different types of limits. So just kind of a quick review. I've got 4 problems here that we're going to take a look at. These two are, they're not 41 and 42 from your assignment, but they're very close to that. They use similar techniques or they're at least along the same lines as those. Okay, so in order to do the problems like this is what most of the section, at least the limits in the section, focus on, are problems like this. Okay, so let's take a look at these and let's remind ourselves. What is this limit right here? Limit as x approaches 0 of sine x over x. That's going to be 1. And do you remember this one? This one was 0. Okay. If you want to grab your calculator and check that out really quick, plug in some numbers that are really close to 0 on either side, that would be fine, but that's what it was. Okay, and we're going to use those limits, and we're going to use a really valuable technique that comes up quite a lot. You may have seen it before, but in a little bit different setting. So here's what we want to do. We want to find the limit as x approaches 0 of sine of 5x over x. Now, the problem with this is our favorite technique for evaluating a limit is, of course, substitution. So if we can directly substitute the 0 into the function on the top and bottom, get a number, we're done. We can just say that's the answer. But of course, we get a 0 on the bottom, and we get a 0 on the top on this one. So we're stuck using those techniques that we've tried before, which on this particular one, we showed this one using the sandwich theorem. I think we did that really quickly, kind of an informal little proof. But this has a very similar structure to this. So if you think about what happens as x gets close to 0, the angle that we're taking the sine of gets really close to 0. And the number on the bottom gets really close to 0, but they're not exactly the same. It would be really nice if we could maybe slide that 5 out front or something like that. You can't. There's no distributing property. There's no factoring of those and breaking them up or anything like that. Okay, so what we do here is a very valuable technique. It's called a change of variables. Okay, change of variables. And you've actually seen stuff like this before. So here's the idea. I'm going to say u is equal to 5x. Because what I need here is I need these two numbers, the angle that I'm taking the sine of and the number that I'm dividing by, I need those to be exactly the same. Like this is an x and that's an x. They've got to be the same in order to use that technique or use this familiar limit like we were talking about here. So we're going to do this. We're going to notice that if x approaches 0, this entire side approaches 0, what does u approach? U's got to approach 0 also. If u truly is 5x, the smaller x is, the smaller u is. Does everybody agree with that? So I'm going to change everything that has to do with an x into a u. So we've agreed that as x goes to 0, u would go to 0. Wherever there's a 5x, I can put a u. So this is going to be the sine of u. And then on the bottom. The bottom is an x, it's not a u, but I need to change everything into terms of this new variable u. So if I know u is the same as 5x, could I replace that x with some expression involving u? Sure. If u is the same as 5x, then 1/5 of u would be the same as x. So now I'm going to make that change. Wherever there's an x, I'm going to put a 1/5 of u, or I'm going to put a u over 5 in this case. So what I've done here is I've changed everything that was in terms of x to be in terms of u. As x approaches 0, u would approach 0. For this part of the expression right here, where there's a 5x, I put a u, because I said u is equal to 5x. And then wherever there's an x, using that same kind of a linear relationship here, I put a u over 5 where there used to be an x. Okay? Any questions there? Okay, so what we've done here is we've changed all of the variables in the original problem to be in terms of a new variable, but everything's still represented the same. Everything still does the same thing. This one approaches 0, that one approaches 0, that one approaches 0. U approaches 0, u approaches 0. U over 5 still approaches 0. Okay, are there any questions? Okay, because from here on out it's easy. It's just algebra. Okay, this was mostly just algebra if you take out the limit idea. So here's what we do. I'm going to rewrite this as the limit as u approaches 0. I'm not going to leave this as a complex fraction. I'm going to flip this over and multiply. Where's the 5 going to end up? 5 is going to end up on the top in the numerator. So this is the sine of 5u over u. Now using those limit laws and the constant multiple rule, I could pull the 5 out front and then times that by the limit as u approaches 0 of sine u over u. Now, what is this stuff right here? What's the limit as u approaches 0 of sine u over u? That's going to be 1. This isn't part of the limit. We pulled it out front, or even if it was, even if we left it inside, it doesn't have a u in it, so it still stays just a 5. So what's the answer on this problem? The answer is 5. Any questions? Okay, so we're going to do the same thing on this next one, but we're hopefully going to do it a little bit quicker. So the substitution I'm going to make here is, again, we hone in on this. What are we plugging into a sine? We need that to be a plain old number, like an x or a u or a z or whatever variable we want to change it into. So again, I'm going to say u is equal to 5x. That means that as x goes to 0, u would also go to 0. So they both approach 0. I can substitute. Wherever there's an x, I can put a u over 5. So this is what I've got. I've got the limit as u approaches 0. This would be the sine of u. And on the bottom, I'd have 7 times x, but x is u over 5. Now, if I think about this for just a second, I'm going to flip that over and multiply all in one step. So this is going to be a 5 on the top, a 7 on the bottom. I've got a sine on the top, and I've got a u on the bottom. And notice the way I wrote that? Kind of a convenient way to write it, because then you can see what the constant is. And let's just talk about in the limit, this doesn't change at all. So that's going to be 5/7. What does this turn into? A 1. So what's my answer? 5/7. It's that simple. Okay, are there any questions? Sure? Okay, let's take a look at the next one then. Any ideas here? Keeping in mind that this is what we know. We know if you have sine x over x, or sine z over z, or sine u over u. Does this fit that form? It doesn't, but we can make it. This is one of those things where we do something that's very counterintuitive. All your life in math you're taught, make things as simple as you can possibly make them. And here, the way we solve this is we make it more complicated. So is there anything wrong with taking this and saying, you know what, I need to have sine of whatever divided by something. So I'm going to take this and I'm going to write this as the sine of, oops, that's a 5x. I'm going to divide the top by x, and I'm going to divide the bottom by x. Is there anything mathematically wrong with dividing the top of a fraction by a number and the bottom of a fraction by a number? No, as long as that number is not 0. And here it's not 0 because we're not interested in what's happening at 0. We're interested in what's happening around 0 because, again, it's a limit, right? So using the limit laws, I can take this and I can break it up into the limit as x approaches 0 of sine of 5x over x, and divide that by the limit as x approaches 0 of sine of 4x over x. Okay, now, we could go through the trouble of doing this. Everybody watch, you don't need to write it. We could go through here and we could say u is equal to 5x and do that same change of variables process here. I could come down here on this one and I could say, well, I already used u. Let's say z is equal to 4x and change all of these variables in terms of z. Or, I mean, a lot of people just use a u on the top and a u on the bottom and then they just make sure they keep it straight. That isn't the cleanest way to do it, but the net effect would be the same. What am I going to get on the top? I'm going to get a 5. I already showed this one over here. We know the answer to the top is a 5. Well, what would the difference be if we went through exactly the same process and that were a 4? It's going to be a 4. So the answer on this one is 5/4. It's that simple. It's a nice little trick of dividing both the top and bottom by x, make it look familiar, use that familiar limit to find the answer. Okay, are there any questions? Okay, you have a couple problems like that. Don't be surprised to see something like that show up on the test. They could put a limit like that on the final exam. They like to make sure that you know all those techniques for finding limits. Change of variables is a very, very valuable technique. We use it a lot. You started using it probably when you were in Algebra 2. You may not remember it. Called it a U-Substitution. We're going to use other change of variables called U-Substitutions in this class as well. Okay, so let's take a look at these two problems. Again, similar in format. Any ideas here? So we're approaching 0. Jason?
Take tangent, break it into sine over cosine.
Great idea. We're really good at working with sines. Well, let's get a sine out of this. Okay? So this we're going to write as the sine of 7x over the cosine of 7x over the sine of x. Questions there? Next step. Flip this over and multiply. So here's what I've got. I've got the sine of 7x over the cosine of 7x. And then, well, let's see, if I flip that over and I multiply, that's just going to make it on the bottom, right? Okay, now I'm leaving off the limit as x approaches 0 just to save some space. Any ideas here? Could we use any part of this to make it look more familiar, make it look like a problem that we've already done? Gordon?
Substitute 7x for u.
We could do a u substitution. We could say u is equal to 7x. Okay, before we do that, I want to do this. I want to arrange it so it looks more familiar. Okay, compare that one, compare what we have right here with what we had right here. We had a sine of 5x over a sine of 4x. Right now, I've kind of got this in the wrong order, so I'm going to write it this way. I'm going to write the sine of 7x over the sine of x times 1 over cosine 7x. Now, can somebody tell me why that is a valuable strategy, especially on this particular problem, to write it this way as two completely separate fractions? Especially considering limit as x approaches 0. Right.
It makes it easier to find the limits for the sine part.
This is very similar to the one that we just got done doing. We had a 5 and a 4 on the top on that other one. Now we've got a 7 and a 1. You might be able to take a guess at what the answer is for that portion right now. So I'm going to keep this stuff, and then I want you to think about this right here. What is this? What do you get when you plug in a 0? 7 times 0 is 0. Cosine of 0 is 1. 1 over 1. This whole thing right here is just a 1. So the final answer for this limit is entirely dependent on what this one is. And remember what we ended up with before. When we had sine of 5x over sine of 4x, limit as x approaches 0, we ended up with 5/4. You want to take a guess at what this one ends up as? Ryan's going to guess for us. What is it?
7.
Yeah, so the first part turns out to be a 7. The second part turns out to be a 1. The answer to the entire limit is 7. And if you wanted to throw that into a calculator and just double check and see, as you approach 0, the function's going to approach 7 from either side. Okay? Again, a little bit of algebraic manipulation and then using a familiar limit. Something that looks like, my gosh, we've seen that before. That wasn't too bad. Okay, any questions there? Sure? Okay, let's take a look at 42 then. Ideas on that one? What's that? It's called, you could use the Pythagorean Identity. So sine squared of theta plus cosine squared of theta equals 1. You could do that. Let's see, so if I need a cosine squared minus 1, that means I'd need to move the sine squared over here and the 1 over here. So that would be cosine squared theta minus 1 equals sine squared of theta with a negative in front of it. Is that right? So this is going to be the limit as theta approaches 0, negative sine squared theta over theta. Good idea? Yep.
Take the power out of functions, like, just sine theta over theta.
Could we take the, let's see, we couldn't take the square out, like totally out of the whole thing because the bottom's not squared. But you're on the right track. How could we make that look like there's just one sine? Michael, break it apart into this. Limit as theta approaches 0, negative sine of theta times the sine of theta over theta. I now have a familiar piece that I recognize. This is going to be 1. And what can you do with this? What can you do with this guy right here? Yeah, you can plug it in. There's no domain issue there. There's no 0 in the denominator. So if I plug in a 0, sine of 0 is 0, so this is 0 times 1. Answer is 0. Okay? There's one technique for doing it. I think, I'm not sure, but I think you could do this one by doing cosine theta minus 1, cosine theta plus 1 over theta, and then break it up into this guy right here. So we'd write this essentially over that one, put that over a 1, and then could you take the limit as theta approaches 0 on this one? That approaches 0. And what about this one? Plug in a 0, you get a 1 for cosine of 0, plus a 1, you get a 2. 2 over 1 is 2. The answer's still 0 either way. Both of those techniques are perfectly good. Okay, are there any questions? Okay, so you've got, I think there are 5 or 6 limits that are assigned on the assignment, and we just did 5 of them, so should be in pretty good shape there. Okay, so we're now going to find the derivative of the sine function. We're going to do it graphically to start with. We're just going to kind of estimate, because remember, that's a good skill to have. Take a function, see what the graph looks like, and then estimate what its derivative or what the slopes of the original function would have to look like. And then we're going to go ahead and we're going to prove it using some of these limits that we've already found here. Okay, so we're going to draw a nice accurate sketch of the sine function here. So our function is sine of x. So remember, that starts at 0, and then at pi halves it's 1, comes back down to 0, hits -1, and then back to 0. So looks something like that, and I'll do a little bit on each side. So we're going to be something like this. These little marks here, I mean, this would be about 1 unit here, because that's about 1.5. Pi halves is 1.57, so it should be to scale. Okay, so this is the function, and down here we're going to graph the derivative, or we're going to graph slopes of the function. Where's the easiest place to find the slopes? Where the slope is 0, okay? Where it levels off, where it flattens off, where it goes horizontal. So there's one, and there's one. So I'm going to come down here and represent that slope of 0 with a point on the x-axis. Slope of 0 with a point on the x-axis. Slope of 0 with a point on the x-axis. Okay, now let's take a look in between here. What do all of these slopes have in common? Okay, so from negative pi halves to pi halves, they're all positive. Okay, now if I draw this in, and I draw a tangent line right there, roughly, just ballpark, what would you say the slope is? Looks like it's about 1, okay? So rise 1 over 1, that looks pretty good to me. So down here, we're going to put a slope of 1. Smaller positive slope here, up to a slope of 1, and then smaller positive slope here. So we start at 0, get bigger and bigger and bigger, closer to 1, and then go back down. What do all these have in common? They're all negative. And if you said that other slope was 1, what would this slope be? Okay, so if we said this slope was 1, we'd have to say that this slope is -1. Okay, or we'd have to say, if we keep in these terms, if f prime was 1 over here, f prime would have to be -1 over here. And then these are all positive. Okay, and in fact right here, it would probably have a slope of +1. So, slope of -1 here. So here's what we've got. We've got this nice curve that just seems to be bobbing up and down as the slopes on the original curve go from 0 to +1, back down to 0, and then down to -1, and then just repeat that cycle. So if this is the original function, and this is sine of x, what does it look like its derivative is? Looks like it's a cosine. Looks like that's cosine of x. Okay, so let's run through here and let's actually prove this. See if I remember how to do this. So the definition, so we're using the limit of the difference quotient, the f of x plus h minus f of x, because that's usually the easiest because we're going to have to simplify here. So we're going to write down that the derivative, let's see, let's just write down limit as h approaches 0, sine of x plus h minus the sine of x all over h. You can never just plug in the point of interest because that's always going to be 0 over 0. So we need to break this up just a little bit. Okay, are there any ideas? Especially with this right here and the fact that you came out of a trig class. What? Can we make this sine of x plus sine of h? Can you distribute a function through to an addition problem? No. Okay, not very many functions allow you to do that. Yes?
You can use sine plus and plus at
The sine of alpha plus beta stuff. Okay, so that is, it's called the sum identity. Okay, so we can use the sum identity. So we're going to rewrite this as, and again, I'm going to drop the limit for the time being. This is going to be the sine of x. Help me out here. Cosine of h. Okay, plus or minus. It's going to be a plus. And then we're going to have the sine of h, cosine of x, minus the sine of x, all over h. Let's see. Ideas? Yeah, Ryan?
Hit the x squared, the sine of x times cosine of h, and you can factor that out, the sine of x from.
Okay, so what he's saying is we're going to collect this term, and we're going to put those together for the time being. So that's what we'll do. So we're going to write this as the sine of x, the cosine of h, minus the sine of x. Okay, I'm going to put that all over h, and then I'm going to do plus the sine of h, cosine of x over h. And then Ryan's suggestion was, once we had that here, we can go ahead and factor out the sine of x. Because sine of x, does it change in the limit? It doesn't. It's a constant, right? So I'm going to rewrite this, and I will bring back the limit at this point. So this is as h approaches 0. I'm going to write the sine of x out front, and then what's left is the cosine of h minus 1. I'm going to write that over h. Is everybody okay if I write it this way? It's the same thing, isn't it? Because that's just over a 1. I could distribute through or multiply through. I'd have the sine of x on top with that other factor, and the 1 times h, still an h on the bottom. Okay, and then I'm going to write plus. Since I broke it into two different parts, I'm going to write the limit as h approaches 0. And then this is, okay, now take a look here. At this point, I'm hoping you can see what we need to do. How do I need to write this one to get this to work out? To get this to be something that looks familiar? What is it, Michael? Sine of h over h times the cosine of x. So let's take a look at what we've got here, and I'm going to change colors. Okay, we're just going to focus in on this stuff right here. What is this in the limit? As h gets closer and closer to 0, hold on, as h gets closer and closer to 0, does that affect this at all? Not a bit. So this is going to be just the sine of x. As h approaches 0, what is this limit? Look up above. It's 0. As h approaches 0, what's this limit? It's 1. And as h approaches 0, does it change cosine of x at all? Not a bit. So this is cosine of x. So here's what I've got. I've got the sine of x times 0 plus 1 times the cosine of x. So that's 0. That's 1 times the cosine of x. So I get the cosine of x. So this isn't just guessing. This isn't just estimating from a graph. If you find the derivative of sine of x, you get cosine of x. The derivative of sine is cosine. Okay, now it would be really cool. Everybody good with that? It would be really cool if the derivative of cosine was sine and we just went back and forth. That would be really great. Okay, it's not, but you can still, we're not going to prove this, but you can guess what it is. So if I graphed in red the cosine function, remember cosine starts up here, goes down, comes back. So it looks something like this. Here's the cosine function. It's a sinusoidal curve, just like sine is. It has that same wave pattern, same period and all that. Okay, so this is the function, and then the derivative I'm going to do in blue. And again, slope of 0 here, got to start at 0. Slope of 0 here has to hit 0 here. Slope of 0 has to hit 0 here and here. So I've got 4 places where the derivative is 0. 1, 2, 3, 4. Okay, I've got those 4 points on there. Okay, now let's take a look in between 0 and pi. What type of slopes do I have? I've got negative. And what's the biggest negative slope I'd have? Negative 1. So I'd come down here, the slope is negative 1. These are all positive. The biggest slope would be at 3 pi halves. It would be positive 1. These are positive slopes, so it would be positive 1. So the graph looks something like this. Whoops, that's crappy. I'll have to fix that. So if the red one is the cosine, that's the original function, and its derivative is the blue one, what does the blue one look like? It's going to be negative sine of x. So the derivative of cosine of x is negative sine of x. Okay. There's an exercise where it actually has you go through and prove it. You do something very similar to what we did here using a sum and difference identity. Now the cool part is, once we know the derivative of sine and cosine, what can you tell me about the definition for tangent? Michael? He's just shy today. It's Monday morning.
Is that it?
What is it? Okay, so tangent is sine of x over cosine of x. In fact, all of the other trig functions are either reciprocals or they're made up of sine or cosine somehow. Okay? So if we know the derivative of sine and cosine, we should be able to use all the other rules that we already know in order to find their derivative. So if I want to find the derivative of tangent, I can find the derivative of sine of x over cosine of x. And notice it says, find the derivative of tangent x using the quotient rule and trig identities. So if I'm going to find the derivative of sine of x over cosine x, I can't simplify that at all, algebraically or anything like that, and I've got it in its simplest trig form, so they're derivatives of functions, or the functions I know they're derivatives. What rule do I have to use to find the derivative? Say quotient rule. It's a quotient rule. Okay, remember, what I said is, when we throw all these together, it's pretty easy learning the derivatives piece by piece, but when you throw all the rules together, that's when it gets more complicated. So this fundamentally is one function divided by another function. So I'm going to use the quotient rule. And the quotient rule is bottom times the derivative of the top. So that's going to be cosine of x times the derivative of the top. Derivative of sine is cosine. Minus the top times the derivative of the bottom. The derivative, so the top is sine of x. Derivative of the bottom is negative sine of x. And the bottom is cosine x quantity squared. So that is the quotient rule. We're done with calculus at this point. The rest of this is just simplification. So if I have a cosine x times a cosine x, I'm going to write that as cosine squared x. Careful here. If I have a negative sine x times a negative sine x, I'm going to write plus sine squared x. And on the bottom I have a cosine squared x. Now, can I cancel the cosine squared with the cosine squared? No, because this is a factor and that's a term. But what can I do? Top's a 1, Pythagorean identity, bottom is cosine squared x. I could leave it like this, but we usually don't leave that as 1 over cosine squared. What is 1 over cosine? Secant, so I'd write this as secant squared of x. So let's run through and let's keep track of all the derivatives that we know so far. So here's what we've got so far. The derivative of sine is cosine. I'm going to change colors. Derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of tangent is secant squared. Now I'm saying secant squared. Of course they don't have any meaning unless you plug an angle into them. So I put an x there. Okay. Derivative of cosecant. I'll just give this one to you. It's negative cosecant x cotangent x. Derivative of secant x is secant x tangent x. And the derivative of cotangent is negative cosecant squared x. Now, you just flat have to have these memorized. There's no getting around it. You're going to see secants in problems. You're going to see cotangents in problems. You better know what their derivative is. Now, sine and cosine are pretty easy to remember. So is tangent, for that matter. But I do want to show you a pattern. Does anybody recognize anything, any patterns in how these are written? Or in particular, their signs? Cosine, cosecant, cotangent. What do they all have in common? They're all negative. All the cofunctions are negative. So the derivative of cosine is negative of its cofunction, okay, in this particular case, so negative sine. The derivative of cosecant, look at the similarities between the two of these. Cosecant is negative cosecant cotangent. Derivative of secant is secant tangent. It's just positive involving those two non-cofunctions, if you will. And the derivative of cotangent is negative cosecant squared, okay? Tangent is just secant squared. Okay, so however you get those memorized, please do. Okay, are there any questions? Okay, then I've got, looks like 7 more problems. We'll see what we can get done in the last 10 minutes or so. I may just do the calculus and then leave the simplification to you. So, what rule do I need to use here? Multiplication. This is a product rule. So here's the first and here's the second. So y prime is going to be second times the derivative of the first, and if you need to put that in parentheses, please do, plus the first times the derivative of the second, and the derivative of the cosine is negative sine. So if I clean this up just a little bit, I'd have e to the x, and I'd have a cosine of x minus sine of x. Easy enough, right? Just pause for a second. A little over a week ago, the only way we could find the derivative was from the definition, from the limit of the difference quotient of f of x plus h minus f of x over h. Can you imagine doing that on this? And yet, this quickly, we have the answer. Okay? So don't forget how powerful those rules are and that you have to have them memorized because your only other fallback is doing it by the definition. And you've got to apply them the right way. Okay? Don't mix up the quotient and the product rule and put a negative where there shouldn't be or a positive where there shouldn't be. Okay? Make sure you keep the bottom and the top straight, the second and first and all that sort of stuff. Okay? How would we need to write this one so that we can do it? You'd have to write it as, I'll write it this way, sine of x times the sine of x. And fundamentally, what do we have going on here? Product. Okay. Now, you go ahead and write down what the derivative would be. See if you can simplify it and just lend an ear. Once you get into trig functions, think about how many different ways there are to rewrite trig functions using identities. That's one of the things that's difficult in this section is you're going to look in the back of the book and you're going to find, holy cow, my answer doesn't look like that. You're going to check your work, you're going to find you did everything right, and it still doesn't look like the back. They probably used an identity to simplify it or at least write it another way. Okay, so please keep that in mind. So if we do the second times the derivative of the first, well, that seems a little bit silly, plus the first times the derivative of the second, whoops, and we get 2 sine x cosine x. Okay, guess what? If you look in the back, is that the answer in the back of the book? No. It's not. They won't leave it like this. What would they write? Sine 2x. That is a double angle for sine. Okay? So if something like that pops up and you're thinking, my gosh, where did they get that from? Think about your identities. Go back and review those. Okay? Fundamentally, what's going on here? Quotient. So we're going to have to do the bottom, just blindly write down the bottom, times the derivative of the top. Derivative of the top is secant squared, minus the top times the derivative of the bottom. Derivative of 1 is 0, derivative of secant. Let's see, derivative of secant, got to get that memorized for right now. Look up above. Derivative of secant is secant tangent. All over 1 plus secant t quantity squared. Okay, are there any questions? let's do a little bit of simplification on this one. Let's see. So I get a secant squared plus a secant cubed minus a tangent squared secant all over 1 plus secant squared. Questions there? Now, it would have been nice if we saw this from the beginning. What do they all have in common on the top? They all have a secant. So let's watch real careful. Secant, I'm left with a secant t plus secant squared minus tangent squared all over 1 plus secant quantity squared. Ideas here? If sine squared of x plus cosine squared of x equals 1, do you remember, isn't there an identity? If you see a trig function squared, what?
I was just saying there's an identity, right?
Isn't there an identity that has a secant squared and a tangent squared in it? Okay, so let's make a tangent squared. Let's divide everything by cosine squared. This would be tangent squared plus 1 equals secant squared. So if I move this over to the other side, I'd have 1 equals secant squared x minus tangent squared x. So wherever there's a secant squared minus a tangent squared, which I have right here, I can put a 1. So this is what I've got. Secant t plus 1 over 1 plus secant t quantity squared. And now, even though these are in the opposite order, it's addition problem, commutative property of addition. I can cancel this one with that one, and the answer is secant t over 1 plus secant t. If that were in the back, pretty tough to see where you go from here to get to there. But again, using identities, yeah.
Would it be simpler just to like make it so it's secant over 1 plus secant over secant?
Would it be simpler to make this so it's secant over 1 and secant over secant and cancel that? Yes, it would. Is that correct?
Oh my gosh, yeah.
No, okay. Ben Gardner, everybody. Okay.
Everyone knows their name.
Okay, Ben, can I pick on you for a minute?
Yeah.
That happens all the time. You guys are advanced math students. You've seen this stuff for years and years, and you look at this and you get in this habit of simplifying and you just want to do something that looks like it ought to be right. If it were 1 plus secant on the top and secant on the bottom, could you do that? Yes, you could. Okay? So make sure you, before you do some algebra or even some trigonometry, make sure it's correct. That whole idea of, I've seen people do this on a calculus test. Okay? So please don't make silly mistakes like that. Okay, are there any questions? Okay. Let's take a quick look at this one right here. Similar type of simplification, but what you've got here is U prime would be, well, let's think about this for just a second. Don't write this down, just watch. Bottom times the derivative of the top. Take a good look at the top. What is it? It's a product. You have a product within a quotient rule. So if we do the bottom times the derivative of the top is going to be the second times the derivative of the first plus the first times the derivative of the second. And I'm already out of room here. Okay? So you'd want to make sure you have plenty of room to write that and then go through and simplify it. I don't think it's that bad. Okay? Yeah, simplificate's a word. Okay. All right, let's take a look at this one. And then I think the rest are not too bad. This one's just going to be a product. This one I say, now what does this mean again? Fourth derivative. Okay, so let's find the first derivative. Cosine of x Second derivative, negative sine of x. Third order derivative, or we do use triple primes. Derivative of this would be negative cosine of x. And what is the fourth order derivative? We're back to, well, the derivative of cosine is negative sine. So if there's already a negative out in front there, we get sine of x. So what would happen with this pattern? How often does it repeat? Every 4 times we take the derivative, we'd get right back where we started. Okay? You've got a problem on your test that's something like, what is the 91st derivative of sine? Well, they certainly don't want you to go through it 91 times. Just think, every 4 times we're back to the same thing. Does this pattern remind you of anything? Imaginary numbers. So if I had I to the 63rd, I take the exponent, or in this case, the derivative we want, divide it by 4, and then think about the remainder. What's 91? Let's see, I could get 20. 4 goes in there 22 times with a remainder of 3. So the 91st derivative is the same as the third order derivative, so that would be this guy right here. It would be negative cosine of x. That's how you'd want to do those problems. Okay? And then the last one I want to take a look at is this one right here. Okay, again, I'm not saying these all are just easy, okay, but we've done enough, I think you can get through these. If we were going to find the derivative here, ideas? Okay, it's a product of 3 separate functions. So you could either think of the first 2 together, and that is the second one. So first and second, or you could think first and second. Doesn't matter to me, okay? So I'm going to do it this way. Here's the first, and here's the second. So dy dx on this one would be, it's the first times the derivative of the second. Derivative of the second is a piece of cake. It's just negative sine of x plus the second cosine of x times the derivative of the first. Now, when we look at the first one, we have to look at this and say, all right, that itself is a product. So then the derivative of the first one is going to be first times the derivative of the second plus the second times the derivative of the first. And the first is 2. And then from there out, it's a bit of simplification. So we'd write 2x with a negative in front, sine squared of x. Here I'm going to write plus 2x cosine squared x. And then I'm going to write 2 sine of x cosine of x. And you might want to look at that and say, do you really think they'd put that in the back of the book? Or is there something you might be able to do with it? If there is, clean it up a little bit. If not, don't worry about it. Okay. Any questions? Okay, for the next class, would you please expand that polynomial and find the derivative term by term? So you're going to have, what is it, 5 terms, 4 terms? 4 terms in the polynomial, find the derivative. Okay. And then I'll show you how to find that derivative another way. Okay. Please make sure you get these memorized. This is the only thing we added today, along with the complication that you could see those in the product rule, the quotient rule, a product within a quotient, or vice versa. Okay? All right. Have a great day.